Hello and welcome to this presentation related to trigonometric proofs. This is the second presentation in the series, and here we consider use of the sine rule and the cosine rule within the proofs we'll be undertaking. There is a previous presentation related to trigonometric proofs where we considered use of basic trigonometry, sine, cos, tan functions, and also Pythagoras' theorem within the proof of various problems considered. I strongly encourage you review this previous presentation as it provides underpinning knowledge and outlines the generic process that we will adopt within the solutions within this presentation. Here's a presentation overview. Commence with a recap of the sine rule, the cosine rule, and various area formulae. Just note for your reference, there are separate presentations related to application of the sine rule and the cosine rule. Then we have example 1b, where we use the sine rule and basic trigonometry to generate two simultaneous equations, which when solved will be able to prove the formula required for example 1b. Then we have question 1b that uses an area formula and the sine rule to generate our two simultaneous equations, which we need to solve to prove the formula stated in question 1b. And question 2b uses the cosine rule and the sine rule to generate the two simultaneous equations required in the solution. Full work solutions are shown to the examples and the questions. And finally you're left with question 3b, which is a self-study question where you will derive your own solution, but the suggestion is to use the sine rule twice in this case to generate our simultaneous equations. And for your reference, here are the approximate start times related to the commencement of the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note these times are rounded to the nearest minute. Here's a brief recap of the sine rule. This slide is extracted from the previous presentation related to the sine rule and its applications. Here is the sine rule, is A upon the sine of A is equal to B upon the sine of B equal to C upon the sine of C. Note the lowercase letters a, b and c relate to side length, and uppercase letters a, b, c relate to the internal angles, which of course all add up to 180 degrees. For reference, I've also shown you the inverted sine rule shown here. Just note for reference, this triangle is termed an acute angled triangle because angles A, B and C are all less than 90 degrees. Recap continued. This is now the cosine rule. I've shown it in this generic form of a squared equals to b squared plus c squared minus 2bc multiplied by the cosine or cos of angle A. Again note, lowercase letters are the side lengths, uppercase letters the angles. I have also shown the rearranged form in terms of cos of A is equal to b squared plus c squared minus a squared, all divided by 2bc. Again, there's a separate presentation related to use of the cosine rule. And the final recap slide here relates to formulae for calculating areas of a triangle. The first formula shown here is the conventional formula, area is equal to half base, lowercase b, multiplied by the vertical height, or sometimes referred to the altitude, symbol h. There's b and h on our diagram here. I've also shown you some alternative formulae. Item 2 here, area of the triangle can be calculated from a half, b multiplied by c, multiplied by the sine of angle A, or in this case B and C are the side lengths, capital A is the angle. And again I've shown some variations in this formula, changing the notation. Item 3 is actually referred to as Heron's formula. This calculates the area of a triangle when no internal angles or vertical height is known, but we're not going to refer to this formula within this presentation. Let's consider example 1b. In the acute angled triangle XYZ, point W is at the foot of the perpendicular from x to yz. Assuming that all internal angles of the triangle and side lengths yz are known, we've got to prove the formula shown here for lengths xw, which is equal to yz multiplied by sine y multiplied by sine z, all divided by sine x. The first step in the process I would encourage you to undertake is to sketch the acute angle triangle, label the angles x, y and z, and then add point W, which is at the foot of the perpendicular from x to yz. Once you have your sketch, you can use the sine rule to find lengths xy, then basic trig, using a right angled triangle to find lengths xw. You then have two equations that you can use to solve simultaneously to prove lengths xw as shown. If you think you can now attempt example 1b, I'd encourage you to stop the presentation and do so. But as a hint on the next slide, I will show you the sketch diagram. So here's the sketch of the triangle, acute angle triangle with angles x, y, z, and here's the perpendicular from x to line yz. So now I'd encourage you to start the presentation and attempt example 1b, but I will show you the full work solution on the following slides. Here's example 1b, commencement of the solution. Step 1, we're going to find side xy using the sine rule. So side xy, shown here, divided by sine of angle z, z shown here, is equal to side yz, shown here, divided by the sine of angle x shown here. Rearranging for side xy, simply multiply both sides of the equation by sine of angle z. We have yz multiplied by the sine of z, or divided by the sine of angle x. And I've labelled that equation 1 for reference. Example 1b solution continued. I've just repeated the equation for xy, equation 1 here for reference. Step 2 of our process, we're going to find side xw using basic trigonometry. So sine of angle y shown here, is equal to the opposite side of the triangle, xw, shown here, divided by the hypotenuse xy, shown here. Rearranging for xw as xy multiplied by the sine of angle y. And I've labelled that equation 2 for reference. What we're essentially going to do now is replace xy shown in equation 2 with equation 1 shown here. We'll substitute equation 1 into equation 2. So the yz multiplied by sine of angle z or divided by sine of angle x is essentially shown here. And of course that's still multiplied by sine of angle y. What has happened on the next line is I've slightly reordered the numerator. I put side length yz in front of sine y, that's in front of sine z. So that's just a reorganization, essentially alphabetically. So that's allowed us to prove the length xw shown in the question above, and this final line is simply showing the same expression but written on one line. That's just for reference really. So we've now proved the length xw as was required. Question 1b. In an acute angled triangle labelled xyz, the internal angles x and z, side lengths y, and the area A of the triangle are all known. Making use of the information given and also the area formula, A is equal to half yz multiplied by the sine of angle x, and also the sine rule, we've got to show the following: that side length x is equal to twice the area divided by side length y multiplied by the sine of angle Z. I would encourage you to stop the presentation and attempt question 1b, initially commencing with a sketch of an acute angled triangle, having angles labelled capital X, Y and Z, and then try and solve the problem as outlined above. The full work solution is shown on the following slides. Here's question 1b, commencement of the solution. Initially we're going to determine side length Z from the area formula as stated in the question. We simply multiply by 2 and divide by y sine x. That forms what's stated as equation 1 here for side length Z. Question 1b, solution continued. Step 2, we're now going to find side length x using the sine rule as stated in the question. So from the sine rule, side length x, shown here, divided by the sine of angle x, shown here, is equal to side length z, shown here, divided by the sine of angle z, shown here. Multiplying both sides by the sine of angle x, then length x is side length z multiplied by the sine of x divided by the sine of z. That's been labelled as equation 2. Question 1b, solution continued. Step 3, we substitute equation 1, stated here for reference, into equation 2, stated here for reference. Notice that sine of x in the denominator cancels with the sine of x in the numerator, from where we can prove that x is equal to 2a divided by y sine z, as stated in the original question. Question 2b, in an acute angled triangle labelled xyz, angle z is known, along with the lengths of side x and side y. We're asked to prove that angle x is equal to the arc sine or inverse sine of length x multiplied by the sine of angle z, or divided by the square root of side length x squared added to side length y squared. Then we subtract 2x y multiplied by the cos of angle z. Once we prove this formula, we're given the numerical values of side length x, y and angle z in radians. We're asked to determine angle x, stating the answer in degrees. Answer shown here in the bracket. So I'd encourage you to stop the presentation and firstly prove the formula stated for angle x. Some hints for the solution. Firstly, I would apply the cosine rule to find side length z, apply the sine rule to find sine of angle x, substitute the first equation formed into the second equation to prove the formula stated in the question for angle x. The full work solution is shown on the following slides. So question 2b, commencement of the solution. So step 1, initially find side z using the cosine rule. This produces equation 1. Question 2b, solution continued. Second step, find sine x using the sine rule. This produces equation 2. Question 2b, solution continued. Finally, step 3, we substitute equation 1 into equation 2. We form this equation. Taking the inverse sines of both sides of the equation, we have our solution for angle x. Again, proving the formula stated in the question. And the final part of question 2b is simply inserting the numerical values given into the above formula. So we calculate angle x numerically. I'll let you review the numerical solution at your own pace. And finally, I'll leave you with question 3b to attempt at your own pace. For A, we have to prove this formula for length PQ. And part B, we have to prove this formula for angle T. As a hint suggests, I would strongly encourage you to make sketches of the various triangles required, clearly label them appropriately. I hope this presentation has been of interest to you, and thank you for viewing.